this is for the energy balance diagram. Energy balance for the closed system. So the first law of thermodynamics is mentioned about the change in the amount of energy contained within the system during the sometime interval equal to the amount of energy transferring across the system boundary by heat transfer during the time interval minus the net amount of energy transfer out across the system boundary by work during the time interval. So this is for the energy balance diagram. Now, about this, thermodynamics is Paramaniama. The snake are chain to quantity chain mass when Suban swine down movie. Eddie swine now the a won't ya a won't we nanomedia your swine down move. Teani about no one swing. A little swine the down kama, people are the logo, no army. A twin swine down a low below kama, twin swine down the boat, no king up here. Suban swine down the move, well yam. Tava this way, Tamu by tiny miss Paramaniama pity. So this is for the example of the thermodynamics. So this will be the model rotating. It can have little marks. So that all the gas liquids are this system. The change of the energy can happen. And so this battery is the supplying the motor. So inside the battery, energy change can happen. So this energy transfer to motor do the work. So this will be the total energy change equal to motor energy change plus a work done. So this is the example of the change of the internal energy. Now, this must be the battery and your motor, the motor, your battery dama, the Lucia Tala, swine down and move, Sulu boundary, motor swine down and move, motor look at alone, and no bound here, battery dama swine down and move. Yeah, Tava swing. The twin swine down the movie, a low look at the Susan swine down the moon, Nidia so there, Tamo time we at Pramania Mao, Jala in Chile. So this will be the when the pressure change, so this original solid state, liquid state, and the vapor state. So the phase diagram. So you can see on the disability dimension, solid state, liquid state, and the vapor state. We can see on this line. So this is the pressure, this is the volume, this is the temperature. The relationship you can see on this graph. Now, let's say a chain down the moon. A PR down the day, do the down the day, a bouye down the day, and I down the moon, set some way at Graco, sweater come a PR down the moon, a bouye down the moon. No, do it. A chain down the moon, and I set some wood in Gratima for that party. Let's say temperature, PR down the moon, graduate up bread. Do the net, no, Piane Pianemu, a gradual bone Povia Pala, Briama pit. So that this will be the temperature and the volume diagram. So this is the temperature line, volume line, and this will be the this graph. So there will be the pressure line. When the pressure change, this will be the liquid vapor. And this one is a vapor. So this is the temperature specific volume diagram. Now, let's say here, not chili down the more Povia Hala. A full change there, Matu Chile, a year actually down the more the Granite Piahare, Tata, let's say, not Pia down the Muline Chile. A down the Muline must be year actually down the Mulio, the Granite Povia Hala. So in this case, we can write down the equation. This is the specific volume, liquid state, critical point, and the vapor. So this is the temperature volume diagram for the water. Dima posing a Puya Hide, PR Hide, and Dima to graph Hide, and Dima swing a chain in Tia Nibuma, the way and if you're a wheel down the Wamu, any chain you would be planet Pogatala. So the next one is internal energy. Internal energy and the be a specific heat of the ID gas. So for the ID gas, we write down the equation. The specific heat is a CV. du by dt means the rate of change of the internal energy. So rate of change of the internal energy equal to specific heat CV. This is for the ideal gas. And therefore, there's a change in the internal energy that du can be calculated CV multiplied dt. So therefore, the change of the internal energy U2 minus U1 equal to CVT dt. So integrate T1 to T2. This is for the ideal gas. As for this constant pressure, specific heat depending on the pressure, CPT equal to dH by dt. dH by dt is the change of the heat and the change of the temperature. So the change of enthalpy and the temperature. So dH by dt equal to CPT. So therefore, the change of this enthalpy equal to can be calculated CPT dt. Now, the internal energy, the enthalpy, the ideal gas, the specific heat, the CVT are a pusa game to the CVT, to the bomb movie, a pusa game, to a balance a twin swine in Piano du by dt, needed, the Jamlu, CVT are du by dt needed, so in du are so CVT net dt net needed, and a twin child swine in Piano you 2 day and U1, no kinzi, CVT Oma, not T1 and T2 to integrate look and needed. And told to the CVT are balance when specific hilo called it a Piavo movie in the a pusa game. And also a twin swine in Piano dH by dt, and a Piano movie in needed. And I'm dH also in CBT dt so H2 and H1 no PR so in CBT dt T1 and T2 integrate look and needed ID gas rate. Imagine probably high in So this is for the controls of volume analysis. Mass flow is a control volume. So in this case, mass rate balance can be also be calculated. Time rate of change of the mass contained within the control volume equal to the rate of flow of mass across the inlet I at the time t minus the rate of flow of mass out across the exit E at the time t. So therefore, the dmCV by dt equal to mi minus me. So the inlet minus AC, you got the dmev by dt. And all the try to down the moody to the zero. Up change the cool tema so the try to be up down the muato, blue less way. When la de try to down the moody, no leana. Try to try to down the no pure quadriame. The Yamlo, Tavalis we change when I see the try to down the moody. The when la de try to be a MIC, try to ME so MI no change. Try to down the moon no dmev by dt so that you may be able to do it. So this will become a stint enter the turbine operating steady state with mass flow rate of the 460 kg/hour. Turbine develops the power output of 1000 kilowatt at the inlet pressure is 60 bar, temperature 400 degrees centigrade, the velocity 10 meters per second at the axis, temperature 0.1 bar, quantity is 90%, velocity 50 meters per second. Calculate the rate of heat transfer between the turbine and the surrounding in kilowatt. Now the mass is the genuine videos will not be turbine when I come up, then I will lead on 12 kilogram when I turbine as we power 2 beta, the town kilowatt 2 beta. I will imagine the PR is 60 bar heated, pushing up 400 degrees in the heated, when I did not as we 10 meter per second heated. A 2 model PR 0.1 bar heated, and 90% swine heated, at 12 watt, I think as we 15 meter per second heated. I don't come up a turbine, but we in a heated, a pushing down and move where I'm heated. So that therefore, that this we draw the pins in the 400 kg/hour. P1 is a PI is a 60 bar, P1 400 degrees centigrade, V1 10 meters per second. And output pressure 0.1 bar, and then this is a efficiency 90%, velocity V2 50 meters per second, and the work time is a 400 kilowatts. So we can draw the spin bars characteristic diagram like this. The winner so we try to see the winner PR here, a Puya here, winner there, I think here, try the PR to no. Now, to try at the end, a beam out at Loshi, the market long so the genuine we are of Alice way, 0.1 bar and 60 bar, a beyond a P. And therefore, that we have to write down the equations QEV minus WEV plus M multiply H1 plus V1 squared by 2 plus GZ1 minus M out multiply H2 minus V2 squared by 2 plus GZ2. So this is the basic equation. And therefore, the QEV can be written by this equation, WEV plus M multiply H2 minus H1 plus v2 square minus v1 square by 2အဲ့တော့ဒီမှာဆိုရင်ပြောင်းလဲမှုအနှုံသားပါလဲဆိုရင်တို့ကနော်ဒီလို QEV ကဘာနဲ့ညီလဲဆိုရင်ထုတ်လိုက်တော့တဲ့အလုပ်နော် WEV တွေကနေ n h1 plus v1 square by v2 plus gz1 minus n h2 plus v2 square by 2 plus gz2 အဲ့ရနဲ့ဒီနှစ်ခုပေါင်းတာကိုဒီမှာ QEV ကနှုတ်တာစုစုပေါင်း0နဲ့ညီတယ်အဲကြောင့်မို့ QEV ရဆိုရင် WEV ရဲ့နော်နော် n h2 minus h1 ရဲ့နောက်က v2 square minus v1 square by 2ရဲ့အဲ့ပေါင်းတာကို m နဲ့မြောက်တယ်ညီမယ်အဲ့ညီမချင်းကိုရေးလို့ရတယ်therefore from the string table diagram we can read out this h2 so h2 sub you can h2 minus h2 minus h2 so that hf2 so that 191.83 plus 0.9 into 2392.8 so we got the 234.4 therefore the h2 minus h1 is 234.4 minus 3177.2 so the one you got and v2 square minus v1 square you can substitute the 50 square minus 10 square by 2 so that 1.21 kilojoule so the QEV is the output plus and that will be that we substitute 4600 kilogram a second this is the mass and this one with the 831.8 we substitute here 1/2 we substitute here and you got the heat can be calculated အဲ့တော့ဒီမှာဆိုရင်သူကစုစုပေါင်းမှာရှိတဲ့အခြေအနေနှစ်မှာရှိတဲ့ဒီစုစုပေါင်းအပူကဒီညီမကြီးနဲ့တွက်လို့ရတယ် HF2 တွေကနေ H2 minus H2 minus HF2 ကိုနှုတ်လိုက်မယ်နှုတ်ပြီးတော့ဒါအစားထိုးလိုက်ရင် 193.83 plus 0.9 minus 2392.8 ဆိုရင် 234.4 ရဒီတာမိုးတွေရောဘယ်မှာဖတ်ရမလဲဆိုရင်ဒီအခြေအနေကနေပြီးတော့ဒီ table ကနေဖတ်ရမှာဖြစ်တယ်နောက်တစ်ချက်ကလည်းပဲထို့အတူပဲမူလရှိတဲ့နော်အပူချိန်နော် H2 က minus H1 ပြောင်းလဲမှုကတော့တို့ဘယ်လိုရလဲဆိုရင်ဒီ H1 က 317.2 ရှိတယ်ဒီအခြေအနေမှာရှိတဲ့စီ H1 ကိုဒါတွက်လို့ရတာဖြစ်တယ်အဲ့တော့ဒီ H1 နဲ့ H2 ဟိုပြောင်းလဲမှုနှုတ်လိုက်ခြင်းအပြင်တို့ကဘယ်လိုရလဲဆိုရင်2345ကျန်နေ317.2ဆိုရင်ဒီတာမို့ကိုရမယ်အဲ့တော့မှ v2 square minus v1 square by 2ကျတော့ v2 က50 v1 က10ပေးတယ်သူ့ကိုစားထည့်လိုက်တယ် 1.2 ရမယ်အဲ့တော့မှဒီညီမရင်းမှာပြန်မစားထည့်တယ်ဒီညီမရ7 h2 ထည့်မယ် h1 ထည့်မယ် v2 ထည့်တယ် v1 ထည့်မယ်drag to n ကိုလည်းထည့်မယ်drag to n ကဒီမှာ460ဆိုပေးပြီးသား h2 ရဲ့နောက်ပဲ h1 ပေးပြီးသားပြီးမြောက်တဲ့အလုပ်ပြီးတော့ဒါတွက်လိုက်တယ်ဆိုရင် QEV ကိုတွက်လို့ရမှာဖြစ်တယ်So that this is for the summary of the second law. Summary of second law means we by using the second law, the direction of the process can be determined, and condition of equilibrium can be determined. Theoretical performance cycle engine otherwise can be known, and quantitatively factor can be evaluated. We can also define the temperature. We can also how user calculate the internal energy change, heat change can also be evaluated. So the second law ကိုအသုံးပြုခြင်းအပြင်ဒီအပူကဘယ်ချိန်ဘယ်ဥတီချက်ကိုသွားသလဲ direction of process ကိုလည်းတွေ့လို့ရတယ်ပြောင်းလဲမှုကဘယ်ဥတီချက်ကိုသွားနေလဲဘယ်အခြေအနေမှာတည်ငြိမ်မှုရှိသလဲနောက်တစ်ခုကဒီလို cycle တွေ engine set တွေနဲ့ဆောင်ရွက်မှုတွေဟိုလေ့လာလို့ရတယ်ထို့အတူပဲအဲ့လိုအကောင်းဆုံးသောဆောင်ရွက်မှုကိုရရှိဖို့လည်းဘယ်လိုအခြေအနေတွေရှိနိုင်သလဲအပူချိန်တွေကိုလည်းကြည့်လို့ရတယ်နောက်တစ်ခါအဲ့ဒီတော့သူ့အတွင်းဆောင်ရင်ပြောင်းလဲမှုအပူပြောင်းလဲမှုတွေကိုလည်းပဲလေ့လာလို့ရမှာဖြစ်တယ်ဒါပါလို့ဆိုရင် thermodynamics second law ရဲ့အကျိုးတရားတွေဖြစ်တယ် So the gaseous statement of the second law means the gaseous statement of the second law is that it is possible for any system to operate in such a way that solely result would be an energy transfer by heat from a cooler to hotter body. So this is the gaseous statement. Gaseous statement ဆိုတော့ဘာလဲဆိုတော့အရာဝတ္ထုကလောက်ဆောင်တယ်ဘယ်လိုဆုပ်လိုက်နိုင်လဲအပူပါဆိုရင်အေးတဲ့နေရာကနေပူတဲ့နေရာကိုနော်အပြောင်းလဲဖြစ်အောင်လည်းပဲလောက်တာဘူးပါမဖြစ်နိုင်ဘူးနော် it is impossible for any system to operate in such a way that solely result would be energy transfer by heat from a cooler to hotter သဘောတော့ဘာလဲဆိုတော့ပို့ပြီးတော့အေးတဲ့နေရာနေပို့ပြီးတော့ပူတဲ့နေရာကိုစွမ်းအင်ပြောင်းလဲမှုမဖြစ်နိုင်စွမ်းအင်ပြောင်းလဲမှုကမဖြစ်နိုင်ဘူးဆိုတာဒါ gaseous statement ကဖော်ပြထားတယ် So therefore we can transfer the heat from the hot to cold that's right but the cold to hot is impossible အဲ့တော့ပူတဲ့နေရာကနေအေးတဲ့နေရာကိုအပူပြောင်းလို့ရတယ်တို့တော့အေးတဲ့နေရာနဲ့ပူတဲ့နေရာကိုအပူပြောင်းလို့မရဘူးဒါ gaseous statement ကိုဖော်ပြထားတယ် So Kelvin plus statement of second law this means that It is impossible for the any system to operate in thermodynamic cycle and deliver a net amount of energy by work to its surrounding while receiving energy by heat transfer for semi-thermal reservoir. The ball of Bales already have two and a pool piano ya unit. Ya unit a yabu to add the child logo meow so the ball pit. Demodi maswing a yabu ya unit kamaswing, two and navio, a look topi bua, material so I'll pop at Hardy. While let's say Kevin's plus statement will call it. So that depending on this thermodynamics property, the pressure and the volume change for the various engine can be plotted on the graph. So this is for the Carnot cycle. From the process 1 to 2, the gas is adiabatically compressed. So the temperature, final temperature you reach. So from 1 to 2 is adiabatically compressed. 2 to 3. So that the assembly placed in contact with the reservoir TH. So that this is the assembly, they are touched with the reservoir TH. So the gas is spent isothermally from 2 to 3 gas is spent isothermally and receiving the Q. So from here it receives this outside heat. Process 3 to 4, the assembly again placed on the insulating stem. So this assembly we put on